Yes, hopefully you are seeing my screen. So welcome again and sorry for the disturbance. Welcome to the Quantum AI monthly series. Today we have very distinguished speakers. We have Dr. Jack Cebulski from Australia, and we have Dr. Mohammed Al-Habash from Egypt. And we all three together, including the engineer Yusuf Al-Dakar, we are going to talk about different applications and the topics in quantum computing and the quantum technologies. This series is hosted by Bibliotheca Alexandrina and also in collaboration with iQafé. And every month we have an edition, and the edition has a theme or a topic to address different quantum technologies or perspective from experts in the field and also experts in the industry as well. We are going to now start with Dr. Jacob Cebulski. Dr. Jacob is a founder and researcher and also consultant at Equanted and honorary associate professor in quantum computing and quantum machine learning at the School of IT at Deakin University in Australia. And also Dr. Jacob will present the need for democratization of quantum computing. Feel free to visit his LinkedIn account and the page to know more about his work and his achievement. And Dr. Jacob, the floor is yours. Please introduce yourself and what made you like the quantum computing in the first place.
Thank you. So should I start sharing the screen?
Yes. And let me if you have any issues with permissions or anything.
Okay. Okay, I'll be sitting half sideways to the camera, so I'll switch it off. Otherwise, you'll see my ear. Well, I'm Jacob Cebulski of Enquanted, Melbourne, Australia, and this is an unusual talk for me. I usually talk about technical things in quantum machine learning, but that topic was sitting on my mind for quite some time. So my earliest encounters with quantum computing, I thought how to make it simpler, how to make it usable by someone walking in from non-physics background, and I am a computer scientist and then working in data science. So this was close to my heart. So the aim of this session is to reflect on the potential problems caused by AI and then consider how quantum technology could be part of the solution. And the problem is the energy crisis. So I'll start with the motivation in this area. Myself, a few words about me. I've set up a small company called Enquanted. It's still being worked out. The website is still a placeholder. And my research and my consulting is in primarily quantum machine learning. I'm interested in dealing with complex data, but I work a lot with time series and signal analysis, but also complex data like graphs and other structured and non-structured data structures. I'm interested also in anomaly detection. So you can see a range of type of data that I'm working on, the temporal models in engineering, in medical science, in business. And because we look for patterns which are complex over a long period of time, we face problems in training models with this type of data. So I'm also looking at what makes those models work and what hampers the effectiveness. In the past, I was looking at having some kind of a quantum advantage, but nowadays I look at utility rather than advantage, and I explain this in my talk. I'm not sure if we have, do you see the borders around the slides or?
Yes, we see black, a bit of black.
Let me just try
line.
to fix it very, very quickly.
Yeah, take your time.
Okay, should be better.
Yes, that's excellent.
So we hear it nonstop. People use AI, kids use AI, scientists use AI to write papers, and I use AI as my research assistant, and everybody's using it, and big companies are training models. And big companies and and countries and their governments recognize that AI is an essential part of the national infrastructure that needs to be supported and protected. And because it's such a widespread use of AI, we have issues. The issue is that training a single large model could take over 1,000 megawatt hours. That's equivalent to 100 homes per year. So that's a lot of energy which needs to be generated to create just one version of it, and not to mention of having updates and continuous updates to those models. So this is a lot of electricity that needs to be made. And AI relies on data centers, and they require energy as well. So in the US, about 9% of total energy produced is consumed by data centers. In European Union, it goes up to 20% of total energy, especially in some European countries. And the AI at the moment is about 15% of that 9 and 20%, and it's projected that by 2030, it will reach 50%. So where is going to come from? Obviously from the grid, and everybody will be affected because electricity companies will not be able to generate so much energy. Another problem is that the US large IT companies, the hyperscalers, they control about 60% of data center capacity in the world, and this will go further up to 70% of global capacity. So in countries, European countries, they rely on American data centers, and in the US is going to be therefore even more demanding to generate electricity. So if AI is going to consume so much power, possibly AI will become the new inequality, hitting the financial aspects and sustainability aspects, and perhaps having impact on the environment as well. If you look at the projections in three major areas in the world, the United States, China, European Union, currently the estimated use for data centers is around, in US, 200 terawatt hours, in China, 140 terawatt hours, in European Union, only 70. And the projection by 2030 is that it will triple. It will triple in the United States and China, but not European Union. Why? Because there's not physical space to put more electricity generating facilities. There's a grid capacity, which is a problem. And so all major European countries are going to have a problem to solve. At the moment, they're simply relying on the US facilities and US data centers to process their data. So it's a fragmentation in European Union. China has a clever policy. They're moving all the data supporting facilities to the east of the country, and the computing facilities, the plan is to move to the western sides of the country where there's a power hubs. So AI and data centers are going to sit on big power hubs, and there should be no issues. The issue is time. Will they have enough time to do it before it becomes critical? In US, it's moving power over the grid to data centers, but there is a lot of investments being made, especially by the hyperscalers, at the moment to buy like crazy small modular nuclear reactors and to revive all nuclear reactors which have been decommissioned. So Google, Oracle, Amazon, Microsoft, Meta, they're all investing in nuclear power. And some of them are more successful than others. Google, by 2030, will have a small modular reactor of 500 megawatts. Oracle, about 1 gigawatts. Amazon is looking for 5 gigawatts. Electricity generation facility, Microsoft, is going to revive the 3 Mile Island reactor, one of the undamaged units. And Trump has just supported it with, I think, about $1 billion to make it work again. So there's actually amazing what's happening, that data companies are buying nuclear power stations. It's science fiction. Does it mean we are entering into energy crisis? Is it going to cause environmental disaster? We don't know yet. I'll give you just two examples of what is facing those companies. Amazon. Amazon was planning to expand the Susquehanna nuclear plant, and it was to connect directly to the data center, bypassing public transmission grids. That would save them about up to 40% of electricity costs, avoiding years waiting in the queue for the connection. However, the Federal Energy Regulation Commission, with some utility companies, argued that during maintenance of the data centers and emergencies, the plant would still need to connect to the grid, and therefore the grid would act as a battery backup for them. And therefore, by not paying the connection grid at that very first time, they are a free rider trying to avoid paying the connection transmission fees, and so they block the plant expansion. So the hyperscalers may be forced to pay their fair share for electricity generation, whether they use the utilities or not use the utilities. It will slow down AI development, but it is democratization of the costs, socioeconomic aspect of it. Meta has even a more interesting case. It was ready to sign the deal with one of the suppliers for the new supercluster, AI supercluster. It would make it the first big tech company to rely entirely on nuclear power. However, this is in the area of the US where old reactors are everywhere. And surveyors are investigating this area and found that in the land adjacent to the planned nuclear reactor, there's a likely rare bee species. So what does it mean? According to Environmental Protection Agency, harming, harassing, or destroying the habitat of those protected species is illegal. So for Meta to proceed any further, they would need to sponsor years of biological studies, then moving the bee habitat, and engage in a lengthy period of time with public comments and feedback. They couldn't wait for that. The project was canceled. So again, the lesson is in democratization, more sociopolitical, of big companies, no matter if they're rich or powerful, they need to embrace the regulatory and physical constraints like anybody else. So there's two cases of democratization and the power of the public over big players. But this is not the type of democratization I'm looking for. I'm more looking at some technological and cognitive rather than social and ethical. I'll explain this more. So first, how is quantum going to play any role in this whole problem? The quantum alternatives, the smart efficiency. So the transition from classical AI, which is energy intensive, to quantum AI, hopefully the quantum AI will be more efficient. Why would that be? Well, first of all, let's reflect. The classical models, like simulating a molecule, take months to train. They use a lot of energy for a long, long time. The quantum equivalent for simulating a molecule, in theory, could take seconds or minutes if such simulation is well designed and is executed on the appropriate device. So hopefully we would get low energy, short duration. Is it possible? So we're looking at two stages of efficiency that could be provided by quantum technology. One is available now, algorithmic efficiency. We could save energy by taking fewer or more efficient computational steps. Okay, is it possible? It depends if we do it right. The second, which is future efficiency, thermodynamic efficiency, which would leverage quantum reversible computation and the Landauer's principle that theoretically it's possible to compute with near zero heat dissipation if the quantum algorithm on efficient machine could be executed. So we have stage one, stage two. The other one is hardware diversity. At the moment, we use superconducting quantum machines, which require cryogenics, and that requires constant and high power to cool the devices. And so we still would get more efficiency if we could get extreme speed of quantum computation. In the future, however, we could shift to devices which could operate in room temperature, such as photonic devices, diamond-based or neural atoms, and we could therefore eliminate some of the cooling energy cost. And we could create the double total energy to solution measurement, fastest time and lower power. The bottleneck is, can we do it right? Okay, who can do it right? All the quantum vendors, they have roadmaps to having more qubits, more power, higher fidelity, but very few people ask the questions, where do we get the drivers for this technology? And IBM perhaps was, and Qiskit were more successful because from several years, they organized large hackathons, large training, free of charge, generating thousands of people with the skills to operate quantum machines, IBM quantum machines. Quantum machines can save energy if they're programmed correctly, but we need much more than that. We need to bring in new workforce. And at the moment, AI is displacing all the data scientists and machine learning experts because AI could do this. Maybe we could bring them into the quantum development tasks. So the implications are we can unlock the energy saving potential of quantum technology, but ideally we should decouple the utility of the quantum machine from the complexity of the underlying physics. And I'm sure I'm talking to a lot of physicists here who understand what it means. So that would mean quantum technology democratization. It is social, it is technological. I'm not looking at ethical issues. This also brings another thing, is that for quite some time we talked about quantum advantage, and perhaps we should start talking more about quantum utility. So rather than saying that would the quantum algorithm achieve an advantage of superiority over classical computation, if we could only match the computational complexity of classical methods, we could gain on the energy efficiency, which very few people talk about. So maybe we should expand the horizons and expand the notion of utility of quantum computing. So let's define the technological democratization, not necessarily quantum at this stage. And let's define a few concepts to differentiate this from other notions. First of all, the notion of specialization. It means some level of mastering. Could be a baker making bread. It's a high renowned specialist understanding how bread grows and bakes, and very people could match the skills of the baker. In quantum area, does it exist, that type of mastery? Yes, we could hire Qiskit programmers. We have tools at the level of this high level of specialization. A lot of those people have PhD in physics, and some people spent years learning some quantum mechanics while being computer scientists. The second concept in massification is meaning ubiquity. For example, the bakery does this. It distributes bread to people so everybody could buy a favorite roll. Quantum need. Do we need to have a QPU in your mobile phone? Probably not. So I think that there's no such urgency to give quantum machine to everybody. Maybe it'll come later, but at the moment, no, there is no need for that. So there must be something else. Democratization in terms of technical and cognitive aspects, how to overcome technical cognitive barriers for using the quantum technology. So utility access. Example, the home cook could get a bread machine, get all pre-mixed ingredients, pour it in, and the next morning everybody eats fresh bread. The bread lovers would benefit. So this is the type of thing we're looking at in a quantum technology. And that probably is high due to the urgency of what should be happening, especially with this energy crisis. And at the moment, there's very few attempts to give quantum technology into the hands of developers who are not physicists, who are not highly trained quantum programmers. So very few tools on the market to be given to those people. Let's look at how the technology developed in other fields. So the ladder of abstraction. I claim that a lot of development, a lot of innovation in other areas is due to the aim of hiding complexity. Let's look at cameras. The initial view camera that you have on the right-hand side, they required a glass plate, the film, and the photographer would get under the hood, manual shutter. He needed to know how long to keep the shutter open, when to close it. And then he was usually the person who needed to know the chemistry to develop the film. And the whole process was to do with the photography with him. Now, later on, of course, we had more miniaturized cameras. And then came cameras with the light meters and rangefinders. Some partial automation happened that people could point and shoot. They still could not develop their own film. They had to go to specialized centers to get the photographs. Now everybody works with a smartphone with a camera built in, and they simply aim and shoot. There is very little knowledge and skill which is required to operate it. So this is sort of massification of photography. The lesson is that what we aim for is that the user focuses on the subject, the machine handles the optics, and this is done. This is available right now. Then we have democratization of calculation, the mathematics. We start with pen and paper, tables of various functions, slide rules. Again, everything was manual process. You needed to have human computers to perform mathematics, simple calculations. And later came calculators, and later graphing calculators, partial automation. Nowadays, we could go to Wolfram Alpha. Everybody has a spreadsheet in their laptop and the tablet. Again, it's for simple mathematics, it's intent-driven. All you just say what you want, and the mathematics is generated for you. So that's a huge jump and leap in the technology of calculation. And then software engineering, democratization of logic. Coding was precise, lines of code specifying what to do and how to do it in assembly language, Fortran, COBOL, and other programming languages. Then came the phase of people using case tools, computer-aided software engineering, and UML diagramming tools to design the logic. And later on, of course, we had business process reengineering and the tools which could establish business rules and then map them onto design and execute them. And so that's happening. Now, in quantum parallel, we would like to do something like this as well. So we are stuck at the moment of coding. We develop circuits and gates, and we have to understand noise, and we need to understand programming. So there's a very complex manual process. And we need to move to specification, which perhaps is domain specific, perhaps in quantum chemistry. Quantum chemistry is so close to what's happening in the actual circuit. So this is easy to bridge. But ideally, we should move into business logic. So we should specify the intent, and that should be mapped onto other areas. So there is parallels in there, and quantum technology is at the moment stuck at the very first stage. So how do we approach this? How do we shift the cognitive load required in quantum development, quantum computing, quantum machine learning? We can learn a lot from what happened in data analytics, because a lot of work we do in quantum computing is analytics. It's analysis of data, and perhaps we have simulations and other tasks, but we could learn from this field. Again, we have a number of stages of development. The era of masters, where people were stitching lines of code with knowledge of linear algebra and statistics, and then using Fortran or C++ to produce analysis of data. And this is where we are with quantum computing right now. You need to understand Hamiltonian, circuits, gates, linear algebra, some quantum mechanics, and some calculus to get results. So there's a baggage of knowledge you need to carry to enter this field. But then in analytics, we had libraries, libraries available in languages like R and SAS, then into libraries available to Python, Pandas, scikit-learn, and then big products, TensorFlow and PyTorch, who can assist data scientists. And then you even have tools which can actually perform those tasks in Qiskit. Like we have Qiskit and Pendelane, where the big libraries are already built into it. So we're moving in the right direction. The levels of abstraction is rising, and then especially it's rising for specialist fields like quantum chemistry or for finance and other fields. Now, what's interesting is that era of strategies, and that was later, after 2010, big analytics companies like SAS and RapidMiner, Tableau, Microsoft, they started building graphical user interface-based tools that someone at the level of business analyst or marketing manager could construct analytic models and execute them without understanding the mathematics of how analytics works and statistics works. We have block box effect. You could drag logistic regression, as you can see on the right-hand side, and then put a workflow with meaningful labels, how to get the data, analyze the data, how to prepare the data, train the model, and then use the model. And then the analysis is done at that level. It's really fantastic. This is the target state. This is where I think we need to be, because then you could engage people at management levels to perform computation with data and quantum computers, perhaps. And of course, there is this AI transformed humans, the polymaths, maybe in the near future, but it's happening right now. So people are using AI for development and analysis tasks. So how do we get a solution? Is it possible? There's two ways of approaching it. Technological development and maybe developing knowledge. And I'll start with the technology. Black boxing and embedding. Moving from being the person composing the circuit to the person who can focus on the problem. Hiding the circuits under APIs. This is happening right now. You have all those SDKs, quantum SDKs, that have specialist libraries for different disciplines. And so if you start developing a quantum machine learning model, you step back from it. You could actually synthesize the circuit automatically or using components, and then you could train it without much thinking about what's happening. That happened in AI before, and to the extent that you simply specify what the type of problem you need to do, and you have those automatic analytic tools that could synthesize the solution for you with high level efficiency. So the tool exists. So we would free the user mental energy from the nitty-gritty of circuit manipulation to focusing on why we're doing it and not the how we need to perform. Now, this may be quite inevitable that this is going to happen with upscaling of quantum devices. So when we now talk about 50 qubits, you could manually stitch out the logic of it. When you have 1,000 qubits, there's no way you could actually produce by hand a viable solution consisting of 1,000 qubits. There must be a different way of doing it, something what happens with VLSI design. In VLSI design, you work with blocks of logic, you put them together, you synthesize the VLSI, and of course you could work with components and developing components as well, but this is large-scale development. This must be happening very soon. Then we have another way of doing it. We could think of having the invisible controller that could dispatch computation to coprocessor, to CPUs and GPUs and QPUs, depending on the task, the mini task to be performed. Like data plotting will require CPU, matrix operation may require GPU, maybe optimization will require QPU, and maybe depending on those devices, you could collect statistics which computation performs better in what circumstances. So the user may not even know they use quantum computer, they simply solve the problem. Now, that's what happens with GPUs and game programming. Game programmers don't need to worry about what happens within the GPU. They simply have modules and the GPU, the game players don't even care if there's a GPU. They usually care because they're faster and they have a better visual effect. But a lot of decisions of what runs in CPU and GPU, it happens in the compilation level. Again, we could have interactive quantum computing and some graphical user interfaces, something like case tools, the computer-aided software engineering, or maybe something like VLSI, depending on the level of abstraction, the scale you're working with. And again, there could be hybrid quantum classical models, something similar to differential programming, like in Pendelane, you could link them together, have very complex models which have components of both types. And user would interactive construct a visual model, simply dragging the objective blocks rather than thinking about if this block belongs to GPU or QPU. So in visual models, they're much easier to work with. They could be worked with by management or some high-level analysts rather than programmers. Now, can we add magic to it? I'm sure we could. We could actually have a conversation with AI about creating a quantum solution, whether those solutions would involve high-level analytic models, UML style, or financial risk models, or if we could incorporate hand-drawn chemical structures or videos of interactions between some components. And this is happening right now. We can actually do almost something like this. AI can understand speech, natural language, diagrams, hand-drawn, simple hand-drawn structures, and videos. So we are not far away from this. Any of those possibilities is happening right now. So we're not talking about science fiction. We talk about a natural extension of existing technologies which currently have not been adopted yet for quantum computing, but we should. A few days ago, I was giving a talk at the workshop in India, and that actually was fascinating because I discovered that the workshop is not just a single workshop. There's a whole series of workshops across India. They are small workshops created by universities and faculties to train their own staff in quantum computing. Where the money is coming from is coming from the government. And the small workshops, there are about 50 people. And people become more aware of quantum computing. They learn hands-on, they have hands-on experience on creating simple quantum circuits and executing them. And even to the extent that now the government in India decided that you need to have a standardized Bachelor of Technology minor degree in quantum computing, which will be taught across India. So there's a policy of on national quantum mission, which is actually looking at bringing quantum computing and quantum technology knowledge into the country. At the moment, India is actually developing their own quantum machines, and they need to have a huge population of people who could actually drive those machines. And it's happening. So at the moment, it's small workshops, about 50 to 60, but within 2 years, they're looking of having the whole host of tier 1 and tier 3 colleges teaching Bachelor of Technology in quantum computing, and they look at having tens of thousands of qualified people able to develop new knowledge in this field. So India is going to lead the world because it doesn't happen in countries like Australia. Now, the other aspect is democratizing access to quantum facilities. And so again, 99% of Indian colleges cannot afford a quantum machine or even access to IBM Quantum. Limited access is given to rich institutes, and some of them may even have some quantum machine, small quantum machines. Now, the government solution is to create thematic hubs and quantum clouds, which would give access, global access to quantum facilities to universities, colleges, and small companies. And so what we're going to see at the moment, we have in Chennai metro area quantum access network. It lets multiple institutions to plug into a quantum network and use it for teaching these students. In Karnataka's Quantum City, they have again quantum cloud, providing access to students in remote colleges. So this is fantastic. The whole policy decouples participation in learning about quantum computing from individuals' wealth. And that's the true democratization of access to those facilities. Then the third is democratization of innovation. And that's happening again in an interesting way. The government is providing grants, they're not loans, to startups. So they encourage creating startups by young innovators and taking risk in developing new quantum technologies, models, and so on. So it's a funding grants for startups. Interesting. So we have technological possibilities and we have knowledge growing possibilities in this space. So we're getting closer to the end, and we started late. So I apologize that we started late. I'll try to be as quick as possible to catch up on time. Let's say we have a viable technical solution to achieving democratization of quantum computing. What's next? What impact? There will be impact on scientists. The scientists could accelerate discovery of materials, drugs, machine models, and without needing the second PhD in physics, perhaps, without maybe the need of learning programming, perhaps. Most of the scientists know those skills, they have those skills. It will give business leaders access to some quantum advantage by simply using the tools they use currently, such as SAP and Salesforce. Maybe those tools could have plugins for quantum computing so that you could simply execute analytics with quantum machines in the background without anybody worrying about what's involved in this. There will be impact on quantum force, shifting from quantum physicists to quantum literate developers. And I think it's at the moment it's happening because a lot of computer science are moving into quantum computing. Now, the risk is that without understanding the underlying quantum mechanics principles, there is actually the risk that people will not understand the impact of decisions being offered by those models, and you could make poor business decisions leading to failure. But the same is happening with AI. So if the bank is taken to court because they made the wrong investment decisions and they wasted customers' money, they have to explain why AI currently in use made the decisions. And that's a difficult task, especially if you use something like neural networks. So we have the whole field learning how to explain the logic of machine learning models, perhaps by creating not the black box, but white box models, not so efficient, but which could partially explain the decision-making process. It's difficult for lawyers to understand. The other problem is the verification. Can we trust the answers given by quantum machines if we can't explain for once? Secondly, if we can't even approach the precision those machines could generate, because classically you may not be able to compute those answers at all. So there's a problem. What do you do about that? It may be a problem with legislation, with the law, and teaching lawyers about those situations. Are those impacts and problems inevitable in a way? Possibly with the scale of quantum machines, some of those democratizations are going to happen as a side effect of working with the complexity. Okay, so definitely if you're working in electronics, if you design a new board for massive supercomputer, you're not going to work with individual diodes and transistors on the board. You're going to have tools to design it in in a proper scale. When it comes to India, yeah, definitely the move from phase one of teaching individual faculty members in universities, having elite labs only for the most expensive universities on facilities owned by institute, to the mass production of people with quantum knowledge, starting with a formal Bachelor of Technology minor degrees, giving cloud access to tier 2 and 3 colleges, and sharing the quantum utility between universities and colleges and even small companies. Okay, so we're moving from low to medium democratization level to medium to high. Okay, so on reflection, what concepts we introduced? First, the abstraction ladder. The history of technology is to do with hiding complexity. Cognitive offloading, shifting focus from the process to strategy and intent rather than the small details of the process. We have some vertical and horizontal access that we talked about, the massification and specialization, but perhaps we also talk about some cognitive and technological access as well. I try to coin the terms of total energy to solution, which could shift the notion of computing efficiency in terms of the energy required to make it happen. And maybe it would be a good way of thinking about that problem. So in conclusion, so we're looking for the green horizon of AI, and we started with a simple motivation of the unfolding energy crisis in artificial intelligence using classical computational methods. Is that an opportunity for quantum technology? Yes, I believe so. I think that quantum technology can be part of the solution to that problem. And the argument is basically that to unlock the efficiency of quantum AI, we need to make advances not only in quantum technology, but also in advances in dealing with the cognitive barriers currently facing people. So hopefully that the shift to quantum AI will be shift towards sustainable high-performance computing and artificial intelligence in particular. So how would success feel if this happened? Basically, I believe that it will be successful if quantum computing becomes invisible in this whole process. And it's invisible, but it will be essential. And like electricity that currently powers AI and quantum machines. Now, this presentation wouldn't be a presentation about AI if I didn't try to incorporate some AI-generated content. This is a Nano Banana Pro trying to illustrate the hiding complexity and adding AI magic. There's some references. The work on democratization of technology, AI, and even quantum technologies. There's prior work in this area, so please grab it. They use a different take on what exactly is democratization process for technology. I looked at different aspects which are not socio-economic, political, perhaps. Thank you so much. If you have any questions, you're welcome.
Yeah, thanks very much, Jacob, for this brilliant and nice presentation. It's very comprehensive report, really covering every aspect and every element, major elements, of course, of the quantum industry and the quantum education. And thanks for touching upon the need for the skilled workforce in quantum technologies, because I think that's very much demanded, and also it's very interested even for developing countries. I mean, in Egypt also there is a lot of interest to develop workforce and for the graduates to work remotely and find jobs as well. So thanks a lot. So I'm gonna start the ball rolling for questions, and then I'm gonna touch upon the quantum workforce because we have several members also who were present in some quantum strategy for education in Egypt, like Asma Safan, Sameh Zaghloul, and Jan Blomert from different places. So the first question is regarding the energy crisis. Now there is monopoly and there is need for the demand for the AI data center from all of this massive need for energy. And would this create a monopoly for big companies to only put hand on the small reactors, the required sources of energies, and this would kill opportunities for new startups to enter the field because they cannot cope with this? What's your perspective on this?
Well, when it comes to nuclear energy, uh, it definitely is going to create opportunities. So the small modular reactors, they're not as expensive as the traditional large reactors. They are modular, which means you could start with one and build up your capacity. So I think that this will open a lot of opportunities for companies, global companies. Except at the moment, there's not many um, companies producing them, but there's some. Definitely, it will open opportunities for uh, global market for energy production. So that's probably is going. In particular, it will be very important for Europe because Europe has no place to create more water energy generation. They did amazing work with wind and with solar, but as we can see the last few years, they struggle with energy to power homes and not to mention data centers. But I think that those small modular reactors will definitely change the world, especially in those countries which are friendly with nuclear energy.
Thanks for highlighting this. Yeah, indeed, the renewable energy in Europe, they also due to the climate change, was not supporting in enough ways and demand for energy. So there's a lot of debate all the time about how much nuclear power you need to put inside the grid to power the home. But of
At the
course,
moment, it looks like the governments are defending themselves from nuclear energy. They don't want it because it's a political issue. It's about winning elections, and that actually means that there'll be more concentration in the U.S. So U.S. is going to dominate the market in data centers, and it'll be hard to compete. And of course, China. So China, U.S. are going to win that race, I think.
and this is in your opinion due to because of these heavy regulations that are there for the environment. So because the other ecosystems are not that confined with these regulations, so they can expand more the nuclear power for the data centers.
Yeah.
Okay, so does anyone have any question? Okay, so while people preparing their minds about question, the second question you mentioned India as an example comparing to Australia. So, in your opinion, what was lacking in Australia in order to dominate? So, the expectation is that India will dominate or lead in the quantum workforce space. What is the lacking element?
Yeah, I think it's an interesting comparison because Australia is a small country, like Canada, perhaps. And Canada started much earlier, and it relied on private industry to move into this field. In Australia, the majority of work was done at universities, and Australia still, when it comes to quantum technology, is in top 10 uh, with Canada, the small countries. Now, when compared to India, India definitely has a much larger economy than Australia, and it's a different approach. So they try to build awareness and the technology ground up, from people on the grant levels. In Australia, majority of government investments in quantum technology was in high-end technology and universities. Um, And so it's a very different take. So Australia is trying to invest in um, high technological and like buying a major share in Isai Quantum, $1 billion spent on that. $1 billion could do a lot of work at the grant level, but it's a different approach. So they hope they're buying big quantum company. It will generate as a side effect the whole infrastructure and logistical hubs and small companies building around. So it's a very, very different approach. But it's hard to say which one's better. It's different.
So it's like a stimulus, this stimulus injection for the economy that would
Yes, yes.
inflate the eco.
In a sense, it's not a socialist approach, it's a capitalist approach,
Yeah,
whereas
definitely.
India is more socialist approach to this problem.
Yeah. Thanks for that. And the third question, for example, if a country similar to India, like in Egypt, there's a lot of interest also for people to learn about quantum computing, integrated in universities, and but there are sometimes limits for funding and for spending on public sector. So, in your opinion, what is the feasible step that any ecosystem in a developing country should take in order to prepare a workforce for these new emerging technologies?
Well, I think it's probably difficult to say for each country. Definitely for governments, they need to take the risk. It's a high risk to invest in quantum technology because there is no immediate benefit from that. So we don't know if it's going to work, how well it's going to work. In theory, it should work, but so far we've seen actually a lot of progress in terms of hardware. But it's invisible. It's invisible to politicians. We know there's a lot of progress. Just looking for what happened 5 years, and today we have a variety of different quantum technologies, completely different, operating on different principles, and hopefully we'll create very efficient machines. But this is not visible to normal humans on the street. They would like to see that we could compute things in 1 second instead of 100,000 years. It's not going to happen anytime soon. But this energy crisis actually could bring us closer because we could see a viable, real benefit in terms of energy costs um, if we could invest in this. I think it
Yeah,
will happen.
yeah, definitely a very interesting perspective. The energy crisis might really push this, hopefully, this to save this demand for energy or reduce it a bit for the
Mhm.
data centers. So
Yeah.
there is
The
a
need, the need will create opportunities. Um,
yeah, definitely.
and
Jan, please go ahead, open your camera and ask a question. Yeah, please. Yeah.
Yes, good afternoon, good evening, Australia. Thanks, Jacob, for a very interesting talk. I was wondering, when you look at AI, machine learning, and energy consumption, uh, what comparison could you foresee between the learning process in AI machine learning and the inferencing?
Mhm.
Deploying the models. Um, because I have the impression, yeah, that when people, and also in your talk, talk about the enormous energy consumption, that there may be a focus on the learning process, yeah,
Mhm. Mhm.
while the business application in practice is about the inferencing, yeah.
Mhm. Mhm.
How do you see that? Could you
Yeah.
comment a little on
Okay. Yeah, I'm a
that?
very practical person. So on LinkedIn, you have a lot of discussions, philosophical discussions. Is it true thinking? Is AI true artificial intelligence? I don't subscribe to any of this. I look at it. Is it a tool which could help us? Okay, so is the inferencing of those AI algorithms assisting us in making decisions? Is it finding knowledge, combining knowledge in new ways? to solve problems for people. So I'm actually using AI for quite some time. I've never had such good research assistant as my paid artificial intelligence. And they're not correct, but my PhDs in the past were completely wrong. So humans make mistakes, AI makes mistakes. A lot of things changes in terms of artificial intelligence. So it's no longer simply large language model which generates answers. There's a lot of technologies going into artificial intelligence in terms of learning and inferencing. So this is a much more complex models that companies are developing right now. So, and one good example was DeepSeek, which put the spanner in the works. And yes, you need to combine those different artificial intelligence technique together to get, first of all, a much cheaper training. Secondly, more effective models at the end. So I think that from what you asked first, you talk about inferencing. I think that there's a lot of work been done on inferencing in artificial intelligence since 1970, and it's gone much further than what was happening in artificial intelligence then. I was doing my master's then, and I thought I was I was learning what's happening. I never conceived that we will have artificial intelligence developed to that extent as now. So I'm looking at it's a tool. It's not a human. It performs the task. It can enhance decision making for business. Definitely, it can. Just people need to be aware that this is not a human. Maybe it's better than a human because it's not driven by emotions and other things. I don't know if that answers your question.
Well, I was more interested in discussing the energy consumption forecast.
Okay.
Yeah.
Okay. So, for example, there's alternatives to what we do now, like neuromorphic chips. They are much lower energy than what NVIDIA is doing. So, and they do they learn how the brain cells work, and they are much lower power that humans use, about 6 volts instead of gigawatts. And I think that we're still exploring the possibilities. So I think that quantum is only one possible way, and there would be those alternative ways of performing AI, which is much more energy efficient. It's people are working in multiple directions at a time. I don't know which one is going to win.
Yeah, I can only agree with that. Um, I would say there will be a lot of effect of these new hardware developments. Yeah.
Yeah. What I hope so is that this.
And it's also a business cost effect. Yeah, you need a
Sure.
return on investment. Yeah, so simply accepting that the energy consumption will go up is not going to happen, I think. Yeah.
No.
Anyway.
But the need drives innovation. So
Yeah.
yeah. So I think that we're being pressed right now by this energy consumption, and at the moment in Europe is done by legislation and regulation, and there must be a better way than that.
Yeah. It's I would say it's not simple, but you could contain in a simple sentence. Business will make rational discussion based on the return on the investment. Yeah.
Sure.
So
Yeah.
and energy cost is part of the cost. Yeah. So that doesn't mean that it's simple, but in
No.
sense, the sense is simple. All right. Thank you.
Thank you.
Yeah, so we have a question in the chat by Mohammed Fergani. How can universities that are not currently involved in quantum computing research begin working in this field?
How can universities, so sorry? Oh,
that are not currently involved in quantum computing, so
okay.
they don't have any ties or anything. How can they start to get involved or start research in this field?
Okay, I'm a good example. I was a computer scientist working in the Faculty of Business, and I moved into teaching data analytics for business students and doing research in this field, initially with data visualization. And I drifted into quantum computing because I thought this is the type of research which is 20 years ahead of us rather than research of what happened 5 years ago. And I think that unfortunately, if you work at the university, the time is pressing you and you need to earn your brownie points in publications. I actually quit the university to do quantum computing because now I can have spent 100% of time on what I think is important. And I love teaching, and that's why I'm give presentations around the world. But I'm doing research as well. So I think it's a commitment of time that very few academics have. And when it comes to technology, technology is available. And when it comes to simulators, they are open source. You could download them. And the workshops, there's a lot of the Q World. There's a big worldwide organization which has the presence in different countries. Like I worked with Q Poland and with Q India. There's workshops of beginner level and advanced level for people who want to learn. So it's only time that you require. And when you need to produce another paper in a star journal, that could be a problem for academics. Universities, the management need to realize that this is an important part, especially if the government puts pressure on investment in this field. It happens in Australia. The government woke up and started investing in big grants around quantum computing.
Okay, so yeah, thanks, Dr. Jacob, very much. Yeah, thanks a lot for the presentation and the nice discussion as well. And of course, if there is more questions, I'm gonna also transmit them to you. Thanks again for being here now with us, despite the fact of all of these disturbances that happen in the evening in Australia and also early morning here. In Europe about the Google Meet crash, but yeah, at least we managed, and thanks for the alert about this.
Thank you.
Yeah, thanks again. And then now we move to our second speaker, Dr. Mohammed Al-Habbash. I'm just sharing my screen.
Good morning.
Yeah, good morning.
Good morning, everybody. Yes.
Yes. And Dr. Mohammed holds a PhD in computational physics from University of Saint Malaysia. Malaysia, and then he would present different applications in quantum sensing. So, Dr. Mohammed, yeah, we are honored to be with us today. The floor is yours. Please introduce yourself and what attracts you also in the quantum computing field before stepping into the presentation.
Thank you, Dr. Salim. And yes, I want to just to share my presentation. I just want to start now. Okay. Just a few seconds.
Let me know if you have any troubles with the permissions or anything. Typically, the permission is enabled.
Okay, I just want to share my presentation now. Do you see?
Yeah, something is coming.
Okay. Maybe I turn off
Yes.
my camera.
Yeah. Now it is there. Now we see it.
Okay. Let us start here. I just want to yes. Okay, let us start with application of thin films for dynamic phase shift generation or generator in optical interferometer and qubit encoding. First of all, I am Mohammed El Habbash, and I have a PhD last year from University of Science Malaysia, and it was in quantum in computing physics. Uh, my specialist is in optics also. I have some research regarding the thin films and to employing the thin films in applications. Uh, as you know, the quantum computing is now is the first or the last topic in computer science. But the main point here that the physics is have a cross or have a shared all the science for because the physics have a majority and have very branches which can share with other sciences. I mean that for computer, for biology, for also for mathematics and quantum computing is one of these. Let us start by investigation the quantum computing in general. Here we have the qubit implementation. There are many type or many technology for implementing the qubit. We have the superconducting circuit, we have the trapped ion, photonic qubits, and the quantum dots, and also we use the natural atoms for implementing the qubits. As everyone, if have anyone start to read or to investigate the quantum computing in general, this is the block sphere, and we have here the state. I mean that the superposition of 0 and 1. We call them a state because we have it is a probability of having 0 or 1 here. As you see here that before we talking about this technology, we have the cosine theta over 2, and also we have the maybe it is wrong here, it is sine theta, not cosine theta. This factor should be 1. I mean that when we make cosine square plus sine square, it should be 1. This is mean that we are stay on the sphere. I mean that the direction, regardless of the direction of the vector, the amplitude will be 1. And the phi is the phase angle. This is the main point that we will talk today about the phase angle, because I will talk about from all these technology, I will choose the photonic qubits. Okay. For the photonic qubits encoding methods, we have now, at this moment, we have the polarization encoding, which means that we will encode the 0 and 1 by the polarization of the light or of the photon or of the wave in general. The polarization, we have electric polarization or magnetic polarization, and we have a mix of them. I mean that a superposition of them. For the path encoding, it depends on spatial, or it depends on the path that the photon will enter. The third one is the phase encoding. This type or this implementation that we will focus today. And we have the spectral encoding, which means that it depends on the wavelength and the spectral of the wave or of the photon. Here we have just a key feature or advantages for each one, or for implementing the qubits using the photonic. We have description for each. You can read it later. I don't want to focus here on that, but I just want to share that the phase encoding is more stable and can be used for long distance quantum communication, and this is most advantage point here. Yes. For phase encoding, we have the interferometry devices. Here I just want to compare the different type of interferometers. We have the Mach-Zehnder, we have the Fabry period, and SNAC, also Young's and Hong-On. These interferometers deal with photons, and each one have their advantage, or their we can utilize them to do something, because some of them are, for example, for Michelson, we have the qubit research, phase difference measurements, and sometimes to generate intelligent states, but also it does not work dynamically. So this is the disadvantage of the Michelson. For Mach-Zehnder, we have the entanglement demonstration, quantum erasers, and the quantum measurements protocols. Also, we have a photonic quantum circuits. This is a advantage for Mach-Zehnder, that we have a photonic quantum circuits, which means that we have a more dynamic than the Michelson. For the Fabry period interferometer, we have the spectral analysis. This point is not in the Mach-Zehnder. Also, we can use a single photon source development and pure quantum light generation. That means that we can implement the a pure quantum qubits. For the Shanks interferometer, we have a spectral analysis like the Fabry period, and we have a single photon source development also, and pure light generation. This is just the technology is different, but it is another type of it. For the fifth one, we have investigating the quantum superposition and wave particle duality. This is advantages is not in the other devices. Here we have, for the last one, we have studying a single photon and quantum exclusion effect and generation for entangled states. For example, for the Michelson, we cannot have an entangled states. This is one of the disadvantages, but also there is another Michelson. I mean that the new generation for Michelson that maybe can utilize this to have entangled states. Here we have the general setup for the interferometers. The black box here, that just to prepare the light, or to prepare the photon to enter the state or the setup. After that, we have the phase shifter or phase shift generation, the orange one, and this one can gives the light there. We can say that the personality or the state of the light. I mean that it will be 0 or 1 depending on the phase angle. the phi. Here you can see that, for example, here the equation below the figure. For example, we have here for 0 states and 1 state that we can have the mathematical implementation or the mathematical expression for the effects of the orange or the phase generator box. The FPS, I mean that the red box, it is the photon loss. It is the photon loss. I mean that we have the photon, we can make losing for 0 or 1, depending on what branch. We have the upper branch and the lower branch. As you see in the equation here, for example, you can imagine that the T0 and T1, it is like a time for 0 signal or for 0 state, and T1 for 1 state. I mean that the upper one is the T1 and the lower one, the lower branch is the 0 state. And the losses means that how much we want the 0 to be, I mean the percentage for the zeros and the 1 states, which refer to the previous equation. I mean that the state, maybe here we have this equation, and we have that, we say that this term, I mean the cosine theta over 2, square of the cosine theta over 2 plus sine theta over 2, all of this should be the summation of this will be 1. I mean that here the losses, we have to distribute the state. I mean that for the 0 and the 1, we can make like a mixing of them percentage, and the final result will be 1. I mean that the percentage for example 50 to 50 or something like this, a mixing or a mixture for state with the state of the qubits. The blue box representing the 50 to 50 beam splitter. This means that we will split the beam, and after that we can measure, and we can, in the green box here, we can define that this is the state 0 or state 1. I mean that qubit will be 0 or 1. This is a general view for the setup for the interferometers. And from the name, it means that there are an interference between them. But this is like a simple setup to understand how it works. For the techniques for shift generation, we have many of them. For example, we have optical path length. I mean that we generate a phase difference by having 2 paths, and by have long, for example, for long path, we have a phase shift, and the short path have a 0, for example, 0 or less phase shift. The other type is electro-optics phase modulators, which depends on the electric field. Also, we have thermo-optics, and we have the delay lines, and we have magneto and electromagnetic effects, which mean that we applying magnetic field to the setup, and we can have a phase shift for these. Also, let us refer to thermo optics and other type, but let us here see that for example, the optical path length modification, we have for that we have the mechanical adjustment for that. We have a classical one, and then we can find another advantage, or the second generation of this type. The first one is like it is like a Michelson interferometers, but after that we use fiber optics to do the same functionality for making the phase shift, but it is have a limited precision of dynamics application. I mean that even we move from the classical one to the more advantage one, but also there is a limitation for dynamic application for that type, which depend on the path length. The second one is the electro-optic phase modulator or generator. The physics behind this is depend on something called Bockel's effect, which means that a linear change in refractive index with applied electric field. As you see here, we apply an electric field, then we have the Bockel effects, which make a change in refractive index. This will change, as you know, the refractive index can change also the phase angle for the light. I mean that the transmitted and reflected light have another phase angle. This provide fast and electronically controlled phase tuning. I mean that it can be more fast and more dynamic. This make us to implement the qubits more fast and to be more dynamic. It is ideal for quantum application and required rapid switching. The rapid switching can be done by electronic circuits. Okay. For thermo-optics phase shifter, this depends on the temperature. In general, I want just to say something. All of these phase generator depending on something called solid state physics. I mean that the solid state physics of the material can change the angle or the phase. Some application depending or some physics depending on thermo features or thermo optics feature that can change the phase angle. Another one depending on electric field. Another one depending on the distance or the length of the path. And we can see also the magneto phase shifter depending on the magnetic field also. This one depending on the temperature, and there is an integrated photonics circuits that can be used. For example, we have here SiO2 that we have a circuit here that can simplify or clarify the situation of how the phase angle will be. But also the disadvantage of this is the slower response, because you know the stream of or the wave of the heat is slower than the electronic devices. I mean that the switch will be more slower. Here we have time bend delay lines. This time bend delay lines, it depend on the time boxes, which can make a phase shift depending on the time bend, and provide phase modulator without direct optical path manipulation. I mean that there is no adjustment of the paths. Anyway, we will move to another one, which is magneto-optics effects. This one also depends on something called or an effect called Kerr effect. the Kerr effect, depending on the magnetic field, which can be applied to the electric or to the photon path or to the light in general, and can change the phase angle. Okay. What is the future work? For us in this at this point, I want just to talk about something which can make a phase generation, but in another, depending on another type of physics. I mean that I will employing here the thin films, specifically the applying a transverse voltage on something or on some thin films will generate a phase shifter or phase shift generator. Here, the first view here, if we have a thin film, I mean that multi-structure thin films, we choose the material for that, and then we apply a transverse voltage. This applying the transverse voltage will accumulate some charge between this material, and thus we can control the phase of the light which will be applying or incident from some point here. You can see that the first layer is metal, but there is some will here that we can applying the incident light, and we can also gather the reflected or transmitted light from the other side. Here, I want just here to say that this is depending on some published paper that we talk or that I published during my PhD. Here you can see that, for example, here 4 layer thin films, and how the light go from one layer to another, and we have like an interface region, which is sigma Z1, sigma Z2, and this region that will accumulate, the accumulated charge will be in these regions. Also, I want here to say that for the material we choose, we have lossy material and lossless material. You can see that this is a Fresnel's coefficients, the transmission and reflected coefficient. The TM refer to the polarization. I mean that this is a P polarization, and TE is the S polarization. Also, you can see here for the lossy material, the refractive index, I mean the N. The refractive index here is the complex number, but in the lossless, the refractive index is the pure or a real number. So this will reflect on the loss of the energy, and also the behavior of the reflected and the transmitted light, or the transmitted and reflected photons when incident on the thin films. In general, the accumulated charge, we have here the conductivity, but this conductivity is not the conductivity that's come from the feature of the material. This conductivity is depending on the accumulated charge. I mean that this is a variable conductivity, which is generated between one layer and the other in the region which that I refer to sigma Z1 and not sigma, it is a delta Z1, delta Z2 in this figure. As you see here, delta Z1, delta Z2, this is the region that we have the conducting or the variable conducting. This type of conducting, depending, as you see here from the equation, on the voltage. This voltage that we can apply all over the system. I mean that from first layer to the last one, and we can change the accumulated charge through this thin films. For our study, I use the periodic product for the polynomial approach, because the polynomial approach can focus on the region or the interface region, and we can here clarify the accumulation of the charge. We have here the matrix, I mean the transfer matrix, which is a part, one of the part is the A and B, or A and beta. The A and beta refer to the interface and the propagation matrix. And here we have the just clarify how is the electric field positive and negative. This refer to the transmitted and reflected. And the Z1 and Zn plus 1, this refer to the layer. I mean that Z1 refer to the first layer, and N plus 1 means that the electric field pass through the vacuum. I mean that they leave the last layer for the thin film. In general, this is the definition of the interface matrix depending on the Fresnel's coefficient, and this equation clarify the propagation matrix depending on the inner product or Hermitian inner product for the wave vector and the distance. I mean the displacement of the electric field through the multilayer structure. After that, we calculating the reflection and the transmission through this mathematics. I don't want to focus on mathematics because we just want to reach to the results. The results here that we have, you can see we have here right, left, and top figure. I mean that the phi r, I mean, it is the reflection phase angle. You can see here, for example, the black one. I mean that the upper one in the figure, the black one, or the black line. When we don't apply any voltage, which means that we apply zero voltage, but the bottom one or bottom line is the bottom dashed red line, is that when we apply 900 voltage. This means that the phi or the phase angle changes, as you can see here, from 10, or we can see 7, maybe 7 degree to minus 12, for example. And you can see that this is this result for a thin films of 2 layer, as you can see here. And also the material here is oxide with calcium fluoride. We have many results for 3 layers, also for 4 layers and 5 layers. I just want here to say that magnesium oxide and calcium fluoride is a lossless material. But what about the lossy material? When we talk about lossy material, everything changes. This mathematics, I just want to let you see how the coefficients, optical and electrical coefficients, it changes from lossless to lossy material, and I mean the complexity of or have a effect on the phase angle and other features for the light. Here we have the result for lossy material with lossless material. We have here the germanium with magnesium oxide. The germanium is lossy material, and the magnesium oxide is a lossless material. Also, we can use another, I mean that we can use germanium with another lossy material. But here we prefer to mix between lossy and lossless material. And we have here also the result, and we can see also that the phase angle changes with the applying transverse voltage. I mean that there is a phase angle shift when we applying the voltage. Here for 3 layers, the same thing, and here for 4 and here for 5 layers. This result, I just want here to refer this for 6. Here just I want to refer to this result that the phase change is not just for one case, for example, lossy material or lossless. I mean that I want to generalize that the applying transverse voltage have an effect on the phase angle. So I have many cases, many fabrication. For example, here we have two layer thin films, 3 layers, and we have mixing between lossy and lossless material. This is that just to generalize that this is not a special case, and we applying a transverse voltage will change the phase angle. Here I want just to start to utilize the phase angle changing to make a phase shifter generator or phase shift generator. Here I choose that magnesium oxide and calcium fluoride just two layer, and here we can see that for the wavelength of 2.5. I mean that the last point on the figure, I refer here to the top right figure. I mean that the phase angle, the phi r for the reflection, because there is also an amplitude r at the top left. I just here want to refer to the top right figure, which is phi r. Here at the point of 2.5 microhertz, the last point in the figure, the top line, the black line here, we have we have applying 0 voltage, and we have here the phase angle, which is we refer to like a 7, for example, it is approximately 7 degree, and we have for the red dashed line at the bottom, we have at the same wavelength, we have when applying 900 voltages, we have for the reflection. The multiplication of this, or to make a difference between these phase angle, we have the delta phi r with 20 degree. This means that we have a new device when we applying transverse voltage will give us a phase shift with 20 degree. If we use another material, maybe we have another phase shift value. I mean that the delta phi r will be more or less. I don't know. This is depend on and the number of layers. Also depending on the applying voltage, which means that if we apply less than 900, then also the result will be different. Here I just want to make a new circuit or a new phase generator, phase shift generator. We have here we have one thin film. We refer to them as one here. I want to use here we have this one. I refer to this one, then the second one, until we have reached to the N1. I mean that when we applying or when the transverse voltage come from here and reflect, then it will reflect from the second 10 films and etc. until we reach here. Then the reflected light here have a delta phi R1 plus delta phi R2 plus until we have delta phi Rn. When we summation this, it will give us a general delta phi R, which will work as a phase shift generation. So the phase shift generation will depend also on the number of the thin films that we will use here. In general, I want just to simplify the circuit. I replace this one by this one. And also because this is, I know that this is a reflection, but I want to make it like a black box. So this is the incident wave or incident photon, and this is the reflected, but I just want to refer to it. It is not a transmitted photons, but we want to use it like this because when we make a circuit, it will be easier for us. Okay. Here we I want okay, I want just to remove this. Okay. Are you with me?
Yes, we are hearing you. Yeah.
Okay, here for the setup of the interferometer, I just want here to refer that for the phase shifter here, we will use another one. I mean that we will use the setup that I introduced. By the way, for this or for this phase shifter, maybe this need to be tested in the lab. Maybe we will not be use the FBS because we can make electronic circuit that can make shifting between lower and upper branches here. I mean that the 0 and 1 by applying or don't applying the transverse voltage. I mean that to give the same photon, sometimes to give them phase angle, and sometimes don't have or don't give them the phase angle. So we have 0 and 1, a mixing of 0 or 1 with the same path or on the same circuit, without having two paths. But this need to be tested on the lab, and this is just a first draft for the idea that can be used in future. I want just here to say that this is like a draft for the next publish, or I will publish this paper solely, but this is like to share with you my thinking or my work on this field. Here, for example, we have I replace the whole system, or I mean the orange one here, the phase. Let us use the pen. I replace this one by this one, and I want here just to, in the next slide, I just use a box, this one, with the have from 1 to n thin films. I use here just two layer thin film. We can use another fabrication, and we have the positive. I mean that this positive is wired to this, and the negative one is wired to this, and also to others, and also here for this one and for this one. But I just I don't want to affect the the electric path, I mean the photon path here. So I remove the wire here. So no need to say that. Just to refer to this terminal. This terminal is wired to these parts, and the orange one is internally. When we're applying the voltage like a pulses with the T0, T0 and T1. I mean the T0, for example, for the bit 0 or the state 0, and T1 for the T1. Then we have a phase shift here. Here you can see we have a phase shift. For example, I refer to it like by or full or half angle. I mean the 180. And for the zero, or for the zero state, we refer to this region. I mean that this is for state 0, and this is for 1. Sorry for the this can this phase angle here can reflect to this one. I mean the state one, and this region is referred to this region, which is the zero, the zero state, and the 0 and 1 is controlled by the voltage. I mean that this voltage, the time for the T0 and T1 will make a mixture of phase angle, and this reflect to state. I mean that we have T1, state 1 and state 0, depending on this voltage. This is a new device that I will introduce, as I say, in a new paper solely, and we will see. I know that there is more challenge about making circuits and gates by this technology, but this is the first step, and we will continue to. Maybe it will be efficient, and also have a diversity of choosing material. This means that we can, when diverse from one material to another, we have more advantages. Also, as Professor Jacob said, that the energy consumption is a more effects or more feature or more variable that we should focus on, or to consider the consumption of energy in general. This is the last slide, and thank you. If there is any, there is also the references for my talk here. If anyone want to see or to refer to my papers or to another papers to see. And thank you so much. If there is any question.
Yeah, thanks very much, Dr. Muhammad, for this nice and interesting talk. Indeed, it is very comprehensive, and it covers a lot of foundational technology from solid-state physics, plasmonics, and towards the latest proposed schemes for having qubits. I just have a question myself to start the ball rolling.
Okay.
So now, would you mind back 2 slides backward?
Which one?
No, the one that you highlighted, the 2 energy level system by the square pulse. Yeah, at the end, the one before, just before the yes. For this one, as far as I see, when you have the state 1, and then the square pulse have a limited time, so you have the duration in microseconds of each square pulse, and then you back to the 0, so you back to phase 0, which represents state 0. And then you jump again to 180 degrees, which is state 1. So my question is, do you have a control over the width of these pulses, so you can increase the coherence time of
Yes.
the phasing? Yeah, just because
Yes.
it might be important for others to know.
Yes, of course, of course. This is, yes, we have a control. This is the advantages of using this technology. I mean that when applying the transverse voltage by pulses, we can control the duration for the 1 and the 0. I mean that the high and low voltages with a specific duration for 0 and 1, and this will reflect on the state. I mean that, for example, I want just to refer to this to the first one. I mean this equation. We have this part and this part. This is not cosine, it is sine. Okay.
Yes. Yeah, that's
Uh,
awesome. Yeah,
yes,
was up to pi over 2 phase difference could be cosine. So
yes.
that's yes.
Okay. Anyway, this part and this part, the square of this part and the square, this part will equal 1.
Right.
We have a mixture of these. I mean that maybe this is, for example, 20 and this is will 80 percentage. I mean, how can we have 20 percentage of zeros and 80 percentage of zeros? This can be done by controlling the width of the time for the zeros and 1. I mean this one, this time. This is the okay. Sorry, I want just to. I mean that here we have the time for 1 and the time for 0. For this one, for example, this T1 and this one is T0. And thus we can control the duration for the state, and we can make a mixture of zeros and 1, I mean the states. So the result of this will be a superposition of 0 and 1. But
Right.
we don't know when we make measurements, then we can decide if it is a 0 or 1, and repeating the system, it can, or repeating the measurements will, after many try, we can decide that, okay, it is the percentage of zeros is for example 20, and for the zeros is 80, and something like this. It depends.
Right.
Okay. Is it clear?
Yes, another question. So, in the superposition, would this mean that this would emulate the real superposition in a sense that we don't know? Because now, if we mix both, it's looked like a classical superposition. So, how the quantum element would appear, the element of surprise in the superposition?
Okay, here, as you see, for the interferometers here, this one,
The beam
this
split.
part,
Right.
the blue one, the PS, the last one, will make a spread for the light to be 2 branches, and at each branch we can make a measurements at the same time, and we can see if it is 0 or 1 at the same point. I mean that sometimes we have a measurements here, for example, and we have a result, so it is 0 now. But at the same time, when we make a measurements here, we make a measurements here, but we have no result, so it is just 0. And if we repeat the same thing, we have 1, for example, at this time, and this is the quantum. I mean that you enter the light from this side with a state like, for example, you have no 0, no 1, and you give a personality or the 0 or 1 or 1 state for this branch, and make this for 0 branches. I mean that when you give the phase,
Right.
the feature of the 1 or the state 1, and this for 0, but you cannot decide if this 1 or 0 at this point, because also the blue box here can split them, and at a specific point, there is also here in this. I want just to refer to there is an interference between zeros and one at this point. I don't go deep to interferometers works, but in this type in the PS also there is an interference between zeros and one.
Mm.
The system is more complex than that. Just it is like electronics. No, the photonics and the feature of photonics and the interference between this branch and this branch at this point will make a quantum or superposition also for the result.
Yeah, thanks a lot. And then a small question, how you would emulate, for example, basic gates like Hadamard. Of course, in photonics it's easy, but I mean, I was talking about the electrical representation, the other representation, how the basic gates could be emulated.
In fact, at this point, I don't. I just want to introduce this new technology for implementing the qubits. After that, I will give the mathematics representation, and I mean the physics representation of the mathematics or the quantum logic or quantum gates by using this technology. At this moment, I just have some ideas in my mind, but I don't want to share because I am not sure about the correctness of the what in my mind, because this is an academic or research should be precise and should be correct. I don't want to share something and after that I find that it is wrong or something want to be updated. So at this point, I don't have I can see I don't have an idea about how we can implement the Q gates, but I am sure that we have as we in the other interferometers, we implement the qubits and also have a quantum gates. We can also, by using this type, we can implement the quantum gates also. But let us it, wait for the time after the idea is accepted by the scientific community, and after that we can move to the second step.
Yeah, that's really great, Dr. Muhammad. I think it's also an open call for collaboration for those who would like to collaborate with you on advancing this idea until the prototype version of it, like until prototyping it. So that's a nice call. Indeed, we have now audience, and also there is also more audience who are gonna listen to the recording, so they might be interested in collaborations as well. So, any question from the audience? Yeah, please, Dr. Mohammed, please go ahead.
I just want to add that I am open and I am welcome for any cooperation for this idea or for this new technology, and also to any other researches. I can share my emails and my contacts. You can contact me using LinkedIn also.
Yeah, so that's really great. So yeah, there's also a concept technology here which is new. So for those who would like to contribute, feel free to contact Dr. Muhammad on LinkedIn, or you can also drop your contact details in the chat as well.
Okay. Yes.
Yeah, take your time. Is there any more questions from the audience? Okay, so if not, I would like to thank my speaker. Thanks very much, Dr. Mohammed Al-Habbash, for the nice talk and nice presentation, and also the technology that you have showed, and best wishes until the technology is implemented and you can see the prototype of this promising qubit architecture.
Thank you so much.
So I have a talk myself. I kept it till the end, but for the sake of time, I'm gonna go through it quickly, just to show you what was the talk was about, and then maybe next time I will give it in full. So I'm sharing my screen quickly. Okay, so the talk I prepared was about quantum benchmarking. It is very hot topic in the market at the moment because it's gives us an idea about the differences of implementations, but also executions between different types of quantum hardware and the platforms, and even technologies and architectures within the same technology. So, in a nutshell, we have the qubit, which already Dr. Jacob and Dr. Mohammed have highlighted. We have the difference between classical bit and the quantum qubits. And the qubits have the ability to be in a superposition between 0 and 1. And would leverage the quantum properties like the superposition. And this is a cinematic view of IBM quantum computer system 1 that was shown and announced in 2019. And as you have seen, it's a very cinematic. So if we open this fridge, this is what we find inside. We find a big fridge and we have a chip that's really in the bottom here. And this chip would contain the qubits. So everything here is about cryogenic. And this cryogenic would control the chip and would load and offload and read, make measurements from the qubits to retrieve the information and read it from after the quantum computations. And when we deal with quantum technology, we have to think about two things. Yesterday, Jan and I, we have already also given a colloquium at ISRO, the Dutch Institute of Space Research, and there we tried also to highlight this as well. So we have differences between the hardware and the software, and also the algorithmic thinking, how to map the problem into algorithm, and this algorithm, how it's translated at the end into a quantum hardware. So this is the idea of the benchmarking. Next time we are going to talk about this in detail, but just this is for the sake of the flow of the story. We have different types of technologies, and like photonic, we have the superconducting, we have ultra cold. There is about 9 to 10 mature quantum technologies at the moment. Maybe there are more, but those are the more popular ones. There are also other technologies still not mature yet or about to be mature, but they are not offered in the cloud, like the topological qubits. There is still also some research around the molecular qubits to use molecules as qubits. And so on. So if we look about how we do a quantum computation nowadays, we are not talking about the theoretical computer science limit. And the theoretical computer science limit, or if we think it as Alan Turing has imagined in his thesis, if you have a machine, this machine will take some steps to arrive from one number to another in a specific sequence. So this is a computation. So the quantum computer is the same. We have a machine, and this machine is capable of doing specific things. In a theoretical limit, you would imagine that everything I do with a classical computer can be done on a quantum computer. But in reality, this is not the case. You need to think of and leverage the existing quantum algorithms. Maybe in the future there will be more developed, or maybe you are going to develop more new quantum algorithms. But so far, we have a specific workflows and algorithms to think of. And for that, if we have a problem that we know classically how it does, because this is how we think, we prepare this problem with a classical algorithm, which is a particular solution of a differential equation or a particular simulation to obtain a result for an atom, and map this problem in a quantum computer or a classical quantum hybrid workflow. So there is some part of the algorithm is done classically, and the major part or some parts are done quantum mechanically or a quantum computer. And then we need to initialize the qubits. Maybe we use them as they are initialized, or initialize them with a specific quantum state, and then translate this quantum algorithm into a quantum circuit. So these gates will act on, and then we perform the measurement to retrieve the results and make post-processing. So this is visually what we see as a quantum workflow. It's very important for the benchmarking to keep this workflow in our mind, because every part of this workflow could be benchmarked and also could be estimated and investigated according to the industry and research standards. So the problem preparation, we have to think about the problem preparation, the type of Hamiltonians that we have. Then we have our classical Hamiltonian. This Hamiltonian is just a function or a quantum mechanical function to describe the total energy of a system. Any quantum system could be described by Hamiltonian, which has a kinetic and potential operators. We are going to see this shortly. And then the mapping, we need to map this problem to a quantum compatible format. This is a hybrid workflow, and then make data loading. We might initialize the qubits in a specific way and then execute it or execute the quantum algorithm to run it and obtain certain results via the measurement. So measurement would collapse the quantum state and then read the classical bits, and then after that we make a post-processing. Okay, so now quickly, what in this talk we are trying to achieve is that the benchmarking of the algorithm design, the benchmarking of the mapping of the algorithm to the quantum hardware, the data loading, the execution, which how this is executed on different types of quantum architectures, and of course the measurement itself, because some systems you can measure them easily, some aren't. And then also the post-processing. What do you need to do in the post-processing in order to link the results that you obtain from the quantum system to the value or the results that you would like to obtain classically. So this is already done in the post-processing phase. So classically, we have a classical harmonic oscillator, and the classical harmonic oscillator, we know it. Next time I'm going to talk about this in detail, but for the sake of time, we have, for example, a system that might move or a mass that's attached to a spring. It oscillates around its equilibrium position, and this spring has a force constant K, and for that we get the potential, which is like a parabola, and then the motion itself make a sinusoidal motion. So this is why we call it a sinusoidal fashion, or it's harmonic motion. So what I call the harmonic oscillator. And then if we go to see, we see a differential equation for that. And then we come to the quantum version. The quantum version of this, we have the quantum harmonic oscillator. And the quantum harmonic oscillator is similar to the classical harmonic oscillator. However, we have the energy quantization. So you get energy, some sort of quantized energy. This harmonic oscillator can describe a vibration of a molecule. So the vibration itself would take certain energies, and here we have the 0-point energy. 0-point energy is the difference between the lowest point in the potential curve and the first ground state vibrational energy. And then we have this quantization. We can climb, this is a Hamiltonian that describes this. Then we can climb using the ladder operator. So we have two representations for the quantum harmonic oscillator. We have the grid representation, which means that we evaluate everything on a grid. So the operators are function of the X, Y, and Z. Here we have one-dimensional harmonic oscillator for simplicity. So it's already expressed in terms of points on the x-axis. And we can also go to the second quantization, where we are treating the quantum levels as steps in a ladder. So we climb them with ladder operators, which are called annihilation and creation operators. In case of the vibration, which is here, we have what's called the bosonic creation and annihilation operators. We have different types of operators called the fermionic operators. Operators in general just can help us climb back and forth between the qubits, so between the different levels. Okay, so feel free to stop me at any second if you have a question. And then we have different types of differences between the fermions and the bosons. I'm not gonna talk about this because of the sake of the time. I'm just giving the workflow of what we are trying to achieve. We have also these different types of bosonic and fermionic operators, and their comparisons is also what we use in executing the qubits. So we have the fermionic, we have two types of particles, fermionic and the bosonic, and then the fermionic have particles have certain properties, the bosonic have another properties, and what we are when we do a qubit system, we want to achieve a two-level energy system that we can control. So we wanted two states that are distinguished from one another. They are orthogonal, so they don't have any overlap, and make them mix in a superposition in a quantum mechanical way. Of course, this is the major types of qubits. We have either bosonic or fermionic. And when we think of a problem, we need to think of it in classically and then transform it to a quantum computer. And if we have our problem in a Hamiltonian, like in a quantum chemistry or physics or a certain optimization problems, there are many transformations that are already implemented in Qiskit. And each one of those have certain complexity. So if we have a molecular Hamiltonian given like this, these ladder operators can be converted into Pauli operators, and the Hamiltonian that we end up with is terms of Pauli strings, so Pauli gates like X, Y, and Z. This is an example, a numerical example for Jordan-Wigner transformation. This is how we do get it. We get these coefficients, and after all, this is what is executed on a quantum computer. It's not directly because there is optimizations that we are going to see in a second. And each mapper of those have certain complexity. So the complexity means that the Hamiltonian, the mapping itself for a single particle or two qubit particle have a certain complexity in order to be able to map all of these numbers that you have into the spin qubit Hamiltonian. So you have classical Hamiltonian, you need to apply this transformation to move it from one form to another. The other form is more suitable to the quantum computer. So this has a certain computational complexity on its own. And there is many ways to optimize this, to use the different techniques for this optimization. And this could be done on algorithmic level and could be done on a circuit level by the transpiler. So the transpiler might reduce the number of gates, might cancel some gates, might approximate some gates. The transpiler would perform multiple approximations in order to achieve a calculation for that. And there is many methods also to achieve optimization using machine learning and AI and generative AI as well. A lot of companies are using this at the moment. We have use cases from Quantinuum. There is also use cases from IBM to optimize on the transpiler level with AI. So there are many approaches. There is also like a GPT VQE, which is like the variational quantum eigensolver powered by GPT. I have two YouTube channels, one of them in Arabic and the other one in English. And the one in English, I have explained the GPT or the generative AI version of variational quantum eigensolver in the English channel. So feel free to visit them. So here we see some examples from compilation or what happened in the quantum transpiler, especially in penny lanes. They use also some kind of optimization. Here is the workflow of the circuit compilation in Qiskit. And after that, once we do all of this algorithmic, we have the good transpilation, we ended up with a very nice optimized circuit. Now it's the time to work with the hardware. And when we do this, we have some metrics for the hardware that we need to take into account while executing some circuits. First obvious thing is qubit count and the quality. The number of physical qubits available in a specific quantum computer that I wanted to run some calculations on the physical to logical qubit ratio. So how much physical qubits I need to group in order to represent one logical qubit. We have two types of qubits. We have the logical and the physical qubits, and the physical are the ones that we use in the lab, and the logical are the ones that we think they are the perfect ones. We use them in our algorithms, and typically there is a ratio between this, depending on the error correction used and several other techniques. And you might end up having a few dozens of physical qubits to represent one logical qubit. So indeed, the physical qubits and the ratio, they are very crucial factors in this. And plus that, you can add on it the error rates. Then we have the coherence time. The coherence time is how much or how long a qubit can take and to decay from an excited energy state to back to the ground state. And this is a coherence time. We have another time called the dephasing time, and this is related to losing the phase, how the information which Dr. Mohammed has showed in the definition of the qubit, the coefficients between the 0 and the 1, they are related to one another. If you normalize, you get 1. So the total state should be normalized, but then the ratio between those coefficients might differ and might be lost. And this is the dephasing time. So the time that the qubit can stay keeping intact the phase information. This is, we call it the dephasing time T2. So we have two important metrics. There are many. Next time we're going to talk about more, but here are the main things. We have also the qubit connectivity and how the qubits are coupled or are connected with one another. So this is a qubit coupling map, and they are very important to perform and might limit also the operation of certain quantum gates, like the swap gate and the CNOT gates, for example. And the different aspect of quantum hardware main property is also the support for native gates. What are the native gates which are already supported by the hardware? If they are not supported, it means that there more approximations have to be introduced and to be used. And we have many more things related to the gates itself. So now we have seen the qubits. Now we go to the gate speed, the readout fidelity, the gate calibration. When you execute or control the gate, do you execute exactly precisely the angles that you have already put inside the gate? Or is there error? Of course, there is inherited error in nature. There's also errors coming from the electronics that perform this, and some noise coming from everywhere in the universe. There's also qubit crosstalks and so on. So we have here the IBM quantum computer, IBM Fizz, and this one is shows this metrics, so we can see those metrics printed, like the coherence time, the dephasing time, the frequencies, anharmonicity, the readout assignment error, the probe measurement and prepare, and so on. And we can look this up in one of the examples of IBM, where you can see precisely if you click on the compute resources, which are available in the inside, then that would give you an idea about what happens from a hardware perspective in the qubit. You can even hover about each qubit here and see more insights about the technical implementation and the metrics of this specific qubit. You can also choose here the different type of gates and so on. So this is for the superconducting qubits. We have different types of technologies like photonic, neutral atom, and also ion-trapped qubits. And those have different metrics as well. I have prepared a presentation which for a YouTube video, hopefully it will be launched soon, where there's more comparison between these different types of hardware. But hopefully this gives you an idea about the workflow that's used, and of course that will be put forward for more discussions in upcoming time as well. Okay, so I think that's enough for now for this. So we can just catch your questions before the end of the event. Okay, so if you have any question, feel free to ask. Okay, then if not, then let's conclude the day. And yeah, I would like to thank you very much for being present in the in today, and also the attendance and all of your questions. And looking forward to meeting you in the upcoming Quantum AI monthly series in December. Thanks for our speakers again, Dr. Jacob and Dr. Muhammad, and thanks for everyone and also for your questions. And see you shortly next version.